This is Physical Chemistry, Part 1, Thermodynamics, Chapter 6, Chemical Equilibrium. Section 6.1, the Gibbs energy G and the Helmholtz energy A. First, the Clausius inequality tells us TdS is greater than dq for a irreversible process. TdS is equal to dq for a reversible process. We can use this Clausius inequality to get some very useful information about the amount of work and its relation with the Gibbs energy and the Helmholtz energy. So let's derive. A is U minus Ts. That's the definition of the Helmholtz energy. So dA is equal to du minus Ts. du is dq plus dw. So we expand du in this way. And then what we do is we combine this dq and TdS. So we have dw minus this thing. And because TdS is always greater than or equal to dq over here, then we can tell dA is always less than or equal to dw. dw is the sum of expansion work and non-expansion work. The expansion work is simply P external dV, actually negative P external dV. Non-expansion work, one example is electricity. If the temperature is constant and the volume is also constant, and then this expansion work is zero. Therefore, we have dA is always less than or equal to this dW, non-expansion work. And if we integrate both sides, the change of A is always less than or equal to the non-expansion work. If there's no non-expansion work, then we say, well, dA is less than 0 or equal to 0. This is the natural direction. Now let's look at the Gibbs energy. At constant temperature and pressure condition, we can do this derivation. G is defined to be H minus Ts, so dG is dH minus Ts. H is U plus PV by definition, and then we can expand du to be dq plus dw. And dPV is actually PdV plus VdP. However, since pressure is constant, VdP is 0. Therefore, dPV is simply PdV. Now let's look at the last term. Because the temperature is constant, so the exact differential of negative Ts is simply negative T ds. So now we have this four terms. Again, we combine this dq and TdS over here. We know this part is less than 0 because of the Clausius inequality. And then we expand this dW to be the sum of non-expansion work and expansion work. The expansion work is negative P external dV. However, this is a constant pressure process. Therefore, P external is equal to P. Therefore, we are putting this negative PdV here as the expansion work. It cancels with PdV. So, the conclusion, at constant temperature and pressure, dG is less than or equal to dW non-expansion. Therefore, if we integrate both sides, the change of G is smaller than or equal to the non-expansion work. Again, one example of non-expansion work is electricity. So if we are looking at a chemical reaction, the change of the Gibbs energy of this reaction is always smaller than or equal to the input of electricity. At constant temperature and pressure, when there's no non-expansion work, that means when this is 0, then dG is less than 0 or equal to 0. Well, this is how we determine the natural direction of a chemical reaction at constant temperature and pressure condition when there's no non-expansion work. Now we learned the three different conditions to determine the natural direction of a process. For isolated system, the entropy always increases. For a constant temperature and volume process, without any non-expansion work, this A, the Helmholtz energy, always decreases. What if we have a constant temperature and pressure process? If the non-expansion work is zero, then G always decreases. Those three conditions are how we determine whether a process is spontaneous or not.